Hello everyone, my name is Tomasz Kostecki and I'm a medical physicist here at Diagnomatic. I've been working with MRI scanners for about 15 years and I would like to welcome you to this Diagnomatic Academy presentation on fundamentals of MRI testing part 2, the annular tests. If you have any questions, write them in the chat and I'll answer them at the end of the meeting. Okay, before we move on, let's briefly recap part 1. Last time we discussed why quality assurance is important and how weekly MRI quality control tests are performed using the ACR Phantom. Today we will continue part 2. We will focus on annual testing, especially the annual tests that can be done using the Pro MRI ACR Phantoms. Before we start, I want to remind you which phantoms we are discussing. Diagnomatic provides Pro MRI ACR phantoms designed for ACR style testing and older Pro MRI phantoms. At first glance, they look similar, so the next few slides show the main differences and how to recognize which phantoms you are using. This table compares the 4 MRI phantoms available from Diagnomatic. The older Pro MRI phantoms have a slightly different design, including more vials and additional wedge structures, but they can still be used for routine quality control. One easy way to distinguish the older Pro MRI phantoms from the Pro MRI ACR phantoms is to look at the wedge structures. The older Pro MRI phantoms have 2 pairs of crossed 45-degree wedges, while the Pro MRI ACR phantoms have 1 pair. Right, so here is the Pro MRI. They have 1 pair, and Pro MRI ACR have 1 pair, and Pro MRI have 1 on each side. The older Pro MRI phantoms have a different internal layout from the Pro MRI ACR phantoms. Because of this, the testing protocol is slightly different. The older Pro MRI phantoms requires 10 slices, while the Pro MRI ACR phantoms requires 11 slices. From this point onward, I will focus only on the ACR phantoms. As shown in the table, ACR phantoms are available in 3 sizes: large, medium, and small. To keep the presentation clear, I will omit the small phantom and focus on the large and medium phantom. This table shows how to select the right phantom for a particular MRI site. The general rule is to use the largest ACR phantom that fits inside the head coil used for clinical brain imaging. The main difference between the Pro MRI ACR phantoms is their size. Because the medium phantom has a smaller internal volume, some of its internal structures are shortened compared with the large phantom. Right, so this is the large phantom, and as you can see, here we have the full wedge, and here we have a little bit cut wedge. Right, overall length is also shortened. Nevertheless, both phantoms can be scanned using the same general protocol, including the same number of slices, field of view, and slice thickness. Before we move to annual testing, let's remind ourselves what is already included in weekly technologies quality control: setup and table position accuracy, center frequency, transmitter gain or attenuation, geometric accuracy, high contrast spatial resolution, low contrast detectability, and artifact evaluation. These are weekly constancy tests which were presented in the last presentation, in the last meeting, and they also have to be done using during the annual testing. And also in the annual testings, additional tests are performed. In this webinar, we focus mainly on the annual tests that can be demonstrated using the Pro MRI ACR phantoms, such as magnetic field homogeneity, at least part of it, slice position accuracy, slice thickness accuracy, and RF coil checks, including SNR, percent image uniformity, and percent signal ghosting. The most crucial and often the most time-consuming part of the procedure is correct phantom positioning. Diagnomatic provides several positioning aids to make this step easier and more reproducible. These include the spirit level, mounting shelves for the levels, and a dedicated cradle. The cradle can be slid directly into the head coil, reducing the need to immobilize the phantom with pads and sandbags. This makes positioning faster, more stable, and more consistent from one quality control session to the next. This image shows how the phantom interior elements can be used for alignment. The phantom is correctly positioned when the laser light is aligned with the superior edge of the grid structure or geometry block, like in the middle picture. If the laser is properly calibrated, this alignment will place the phantom correctly at the magnet isocenter after it is moved into the scanning position. After positioning the phantom, we acquire the ACR sagittal localizer and axial phantom series. The exact sequence parameters are important because changes in slice thickness, gap, field of view, matrix, etc. can change the measured results. Right, so those are the this is the table acquired from the ACR page. I will provide the link at the end. The next step is to plan the axial series on the sagittal localizer. The ACR protocol uses 11 axial slices. These slices should be positioned carefully using the centers of the slice locations and not the slice outlines. Correct slice positioning is important because if the slices are shifted or tilted, the measurements might fail even if the scanner itself is working correctly. The bicycle slice should be positioned at the inferior wedge, close to the chin side of the phantom. In the ACR description, this is usually treated as slice 1. Right, so this is slice 1. Sometimes the system infers the numbers, so the slice 11 lands in this place, but keep that in mind, we'll be referring to this as slice 1. A simple way to check correct positioning is to look at the first slice, the resolution slice. The two wedge structures should appear at the same height, right? So this is the same height, and this is slightly, this is very very much moved position. If they are not equal, the slice position or phantom alignment might need correction. So this is an exaggerated visualization of the bad positioning of the slice. The first annual test on the ACR list is magnetic field homogeneity. This text checks the uniformity of the main magnetic field, B0. It is usually performed with a uniform spherical phantom, often provided by the scanner manufacturer. So it's not ours; it's the scanner. It's the phantoms provided by the manufacturer. Percent image uniformity, or PIU, should not be considered with magnetic field homogeneity, right? So this is an important message. B0, or magnetic field homogeneity, measures how uniform the main magnetic field is. Percent image uniformity measures how uniform the image intensity is. Percent image uniformity is influenced mainly by the radio frequency coil, receive chain, image correction, phantom positioning, and artifacts. Poor magnetic field homogeneity can affect images, but percent image uniformity is not a direct B0 homogeneity test. In this presentation, however, we are focusing on tests that can be performed using the Pro MRI ACR phantom. The Pro MRI ACR phantom is not usually the main phantom for this test, but it can still help with one practical part of the bandwidth difference method, estimating the full received bandwidth. This is useful because scanners might report bandwidth in different units, such as hertz per pixel, full bandwidth, half bandwidth, or fat water shift. If the bandwidth value is unclear, we can use slice 1 of the Pro MRI ACR phantom This slice contains a fat-water insert. Because fat and water resonate at slightly different frequencies, the fat structure is shifted relative to the water structure in the frequency encoding direction. By measuring this shift, we can estimate the full received bandwidth value. Okay, so as the construction in the actual construction of the phantom, the walls of those compartments for the fat and water are usually at the same position. So if we measure left and right, we can estimate the bandwidth of the scan, and using, of course, this equation. Next, we move to slice position accuracy. This test checks whether the scanner places slices at the prescribed positions. In the Pro MRI ACR Phantom, it is assessed using the crossed 45-degree wedge structures on slices 1 and 11. If the slice is correctly positioned through the wedge vertex, the two dark bars should appear equal in length. Here we see the practical rule. The wedge bars should have the same length. If one bar is longer than the other, the slice is displaced superiorly or inferiorly. The bar length difference is measured and used to estimate the slice position error. Okay, and this is how the phantom is constructed. The wedge structure is easier to understand in the sagittal view. It's made of two adjacent angled elements, right? So this is element 1 and this is element 2. When we put them together and perform a 1 centimeter or 2 centimeter sagittal scan, we can see this image, right? So this is this part of the phantom. In this schematic, the blue slice cuts the wedges in a position where the two bars are almost equal, right? So here is the wedge size, right? And it goes almost right here to the middle of the vertex. The orange slice cuts one wedge in a shorter point and the other at longer point, right? So this is where the difference in the wedges comes from. When the slice is in the correct position, the two wedge bars are almost the same height, right? If the slice moves in the Z direction, it intersects the two angled wedges at different positions, so one bar becomes longer and the other becomes shorter. Even small slice planning errors can be visible here. One thing worth checking is whether the slice was positioned using the center of the slice, not the slice outlines. Using the slice outlines for planning is a common mistake, and it can shift the slice slightly from the correct position. The action limit for slice position accuracy is based on the bar length difference. The difference should be 5 millimeter or less. Because the wedges are angled at 45 degrees, a 5 millimeter bar length difference corresponds to an actual slice position error of about 2.5 millimeters. If the result is outside the limit, repeat the scan with careful slice planning before assuming scanner failure. Okay, so step 1, check if the slice prescription is correct, right? If the error has the same sign and similar size on both slices, the first one and the last one, the first and the 11th, table positioning error might be involved, right? So the full table moved slightly too far or too close, right? Other possible causes include gradient calibration problems and magnetic field inhomogeneity. If the cause is not clear, service support might be needed. Next is slice thickness accuracy. This test checks whether the measured slice thickness matches the prescribed slice thickness. It's performed on slice 1 using 2 crossed signal ramps. The ramps are inclined at 10:1 slope, so the visible ramp length is related to the actual slice thickness. Right. So this is a cut from the slice 1. Here, if we adjust the window and level, we can see those ramps in the image. Mhm. Okay, so after adjusting the window and level, so the ramps are clearly visible, measure the top and bottom ramp lengths. Both measurements are used in the formula, which helps compensate for small right-left phantom tilt. For a prescribed 5 mm slice, the ACR criterion is 5 mm plus or minus 0.7 mm. If slice thicknesses fails, the cause is usually technical rather than simple ROI placement. Possible causes include radio frequency amplifier nonlinearity, this distorted RF pulse shape, RF power amplifier, cable switch or transmit coil problems, poor gradient calibration, or poor gradient switching performance. Because the problems can affect image quality, a failed slice thickness result usually requires service investigation. Of course, redo the scanning and then call the service, right? The next group of annual tests is the radio frequency coil checks. A useful practical point is that sagittal to noise ratio, percent image uniformity, and percent signal ghosting can all be evaluated on the same central uniform slice. So we just take the same slice and we do 3 tests with it. In the Pro MRI ACR Phantom, this is usually a slice 7 of the ACR T1 series, T1 weighted. The slice is the same, but the ROIs and the purpose of each measurement is different. The first coil check is signal to noise ratio, or SNR. SNR tells us how much useful signal we receive from the phantom compared with the noise in the image. For the mean signal, place a large ROI inside the phantom, covering at least 75% of the phantom cross-sectional area. Right, so this is the first ROI. For the noise measurement, place an error ROI outside the phantom, preferably in the frequency encoding direction, and avoid ghosting, edge truncation, RF leakage, and filter background, right? So no artifacts here and here. We can place more than one noise ROI. On the next slide is an equation how to calculate it. On the slide, we can see how the ROIs are placed on the SNR measurement. This is a larger image, sorry. Okay, let's get back. The large ROI is measured for the mean signal in phantom. And here is an equation for converting the standard deviation of the two ROIs of the similar size into one standard deviation combined, which you then add here. Now we move from SNR to percent image uniformity. We still use the same central uniform slice and the same large mean signal ROI inside the phantom. Right, so this is the one. Image is quite different, but it's still the same ROI. To make this easier, set the window with first we'll look for the brightest region inside the large ROI. Right, so we have to adjust the window and see for look for the region of pixels with the highest value. Place a small measurement ROI over this bright region. The small ROI should be approximately 0.15% of the field of view area. About 1 square centimeter for a 25 by 25 centimeter field of view. And this is the field of view prescribed by the ACR sequences. Record the mean value as max ROI. Next, we find the lowest signal region inside the same large ROI. Adjust the window level in the opposite direction so that only a few dark pixels remain visible inside the large mean signal ROI. Place the same size small ROI over the darkest region and record the mean value as mean ROI. PIU is calculated from the max ROI and the mean ROI values. Do not use single maximum or minimum pixel values. Right, so it always has to be the average. The last coil check is percent signal ghosting. Ghosting is an artifact where a faint copy of the phantom appears outside the main phantom, usually in the phase encoding direction. For this test, we use the same slice. We use average signal from the main phantom ROI and then place 4 background ROIs outside the phantom. Top, down, left and right. The ROIs in the phase encoding direction measure ghost signal, and the other ROIs act as background controls. After recording the 4 background ROI values, we calculate percent image ghosting using those ROIs. The formula compares background signal in one direction. Okay, and the main information in this slide is if the result is reported as a ratio, the action limit is 2.5%, right? If the test fails, first check the phantom motion or vibration. So don't call the service. Just try to fix the phantom a little harder. Use more sponges and belts. If the phantom was stable, ghosting may indicate receiver, transmitter, gradient, or other hardware instability. The last part is about recording the result. This is not only about writing down a number. For annual testing, we should keep the images, measurements, ROI, placement, scanner information, etc. All together, right? A good quality control record should answer 3 questions: what was measured, how it was measured, and how it compares with the previous results. This is why, if you are interested in a pro MRI ACR phantoms, I also encourage you to consider Diagnomatic online. It helps keep the images, measurements, reports, and trends in one place. So the next annual test is much easier to review and compare. Also, it can be run on your cell phone, so it's always available. Okay, these are the links I used for this presentation.